physics friends. Today I am going to be walking through AP Physics C Mechanics free response question number 3. And I'm going to not only just solve it for you, I'm going to tell you what exactly it's asking, because sometimes the wording is a little tricky and that's what trips up a lot of people. So, let's start by reading the question. A ring of mass m, radius r, and rotational inertia mr squared is initially sliding on a frictionless surface at a constant velocity v prime to the right, as shown above, right here. At time t equals 0, so right here, t equals 0 corresponds to this position, and also at this time, it encounters a surface with a coefficient of friction mu and begins sliding and rotating. So right here it is sliding and rotating for the duration of distance L. After traveling distance L, the ring begins rolling without sliding. Express all answers to the following in terms of m, r, v prime, mu, and fundamental constants as appropriate. So fundamental constants are like g, such as, gravity, as everyone knows what that means, and it's, a fundamental constant for an Earth system. So, part A, starting from Newton's second law in either translational or rotational form as appropriate, derive a differential equation that can be used to solve for the magnitude of the following as the ring is sliding and rotating. Okay, so it asks for a differential equation that can be solved for I and I 1 and 2. Alright, so it says we need a differential equation that can be used to solve for the linear velocity of the ring as a function of time. So that means the change in linear velocity, right, with respect to time. So that is written as dv dt, as we learned the derivative of velocity with respect to time. So that is what we are trying to get here. But first, how do we get here? Well, we have to look at what we know. We know that there is a change in linear velocity. How do we know that? Because there are unbalanced forces as the ring is sliding and rotating. Okay, so it's asking along distance L when it's sliding and rotating. The question tells us that we now come across a force of friction, and which is pointing in the opposite direction of motion. So the force of friction is pointing this way because the motion is that way. So now we know we have the force of friction and we don't have any other forces. Pretty neat, pretty simple. So when we have just the frictional force, it's unbalanced, and we know from Newton's second law that F net is equal to the mass times acceleration of a system. And because friction is the only force here, it is the only unbalanced force, the force of friction is equal to mass times acceleration. Pretty simple. Now we also know that F equals mu mg. And now we know that we can have mu, m, and g within the final equation, any of these, except for acceleration. Because it says express all answers in terms of m, r, v prime, mu, and fundamental constants. So we have mu right here, m here, and g is a fundamental constant. And for F net we have m, but we have acceleration here, and we can't express this in terms of acceleration. And also, we're solving for dv dt. So, ooh, what? Oh, yes, yes. The acceleration, as we know, is equal to the derivative of v with respect to time, the change in velocity over time. See, if we reason that out, acceleration is the change in velocity over time. So if we have, oh, we also can't express the final answer in terms of f because that is not one of the terms given. So we have f here and f here, so let's just set them both equal to each other. The masses cancel, and then we have a, and we're gonna plug it into here. So dv dt is equal to mu g, and oh, I'm very sorry. This is going to be negative the whole time because it's in the opposite direction of the motion. So sorry. Do not forget this negative. So, linear velocity of the ring as a function of time, dv dt equals negative mu g. That's what the question is asking. It's not that scary once you get used to it. Okay, next they want us to solve for the angular velocity omega of the ring as a function of time t. So, angular velocity is just like linear velocity, but it is different because it is angular velocity is the rate of change of theta over time. Linear velocity is the rate of change of straight linear x or L distance over time. So here we go. Angular velocity omega as a function of time t. So I'm just going to fold this over, sorry, so that we have more room to work with. We have very little camera space. Okay, A part 2. Okay, for this problem, you are going to need to know that, well, okay. Remember in the last problem, we labeled this and we said this was the force of friction and it's going this way, even though the motion's going this way. Isn't the force of friction, so, isn't the disc only touching here at a time, and here is going to be right directly from the center, and it's going to be going straight down. And so this is our mass. Yep. Okay. This is sorry. This is the point of contact, and this is the force vector. I didn't draw it so great, but isn't the force not parallel, perpendicular with the point of contact of the disc? That force that is perpendicular to the point of contact, to the disc, is called a torque. So the frictional force is a torque. And here you are going to need to memorize this equation. Torque equals the moment of inertia times alpha, the angular acceleration. So we established that force is the, and then they give us that the rotational inertia is mr squared. So torque equals mr squared alpha. Torque is also equal to friction, which is equal to, mu mg. Times R, because torque is measured in Newton meters, so we have to take the force and multiply that by the distance from by the radius. Okay, so torque is equal to mu mg r. Now we know that angular acceleration is the change of omega, angular velocity, with respect to time. So we have here, here we go. So we take these two equations, we take mr squared alpha, equal to mu mg r. So let's try to get alpha to one side. So alpha is equal to, here the mu's cancel. I'm trying to do this in my head, sorry everyone. We have, wait, okay. Oh my gosh, Sophia, let's see. Okay, we're just gonna do mu mg r over, sorry, is that a mu or, no, that's an m, okay. I'm sorry about my handwriting, I apologize. So the m's cancel, so this is going to be mu g over r. Yep. All right, and so we know that alpha is the change in alpha is the change in angular velocity over time. So we just, and it wants a differential equation. Yep, right there, differential equation. So we just substitute that in. Oh, I am so sorry about my handwriting. O is equal to mu g over r. And that is our second differential equation. Hey, so we're done with part A. Just a few more parts to go. 4 more parts to go. All right, part B, part 1. Are you guys ready to do some light integrals? Yes, you are. Okay. Derive an expression for the magnitude of the following as the ring is sliding and rotating. The linear velocity v of the ring as a function of time t. Well, we already did something like this right here. We already solved for dv dt is equal to negative mu mg. No, negative mu g. Sorry. Okay. So let's just write that down here. dv dt, the change in velocity with respect to time, is equal to negative mu g. Now let's just multiply both sides by dt, just for fun, Okay, so I see the derivative of velocity is equal, and a derivative of time here. So what are we gonna do? You know what? Just for fun, let's integrate it. Okay. So dv from let's say v0, because that makes sense. V0 is the starting. to v, which is the ending. Oh, hey, look, that's what we're solving for. The ending velocity is equal to, see, we could, since a negative is always constant, we can bring this negative to the front. Integral from 0, t equals 0 to t mu g dt. So, the change in velocity, dv, from v0 to v, the change in velocity, well, that's just final minus initial velocity. See? Okay, now the coefficient of friction is a constant, so we can bring that up here. Gravity is a constant as well. dt from 0 to t is just final minus initial, t minus 0, just t, so it's equal to negative mu gt. And v is equal to, let's see, we add v0 to both sides, minus negative v0 minus mu gt. Hey, look at that! We found it. The linear velocity of the ring as a function of time t. Look at that. Look at that. We're superstars. Wasn't too bad. Wasn't too bad. Look at that. That's integration. You did calculus. Good job. Oh, sorry. Sorry. This was part 1. This is part 1 of B. Sorry, everyone. On to part B, part 2. Derive an expression for the magnitude of the angular velocity omega of the ring as a function of time t as the ring is sliding and rotating. Okay, so the angular velocity omega. Hey, just like in part B, part 1, we had this equation. Let's see if we can figure out part B, part 2 using this equation. Spoiler alert, we can. Yay. Okay, so we are going to do almost exactly what we did with the other one. We are going to, oh, okay. I'm just trying to, we have d omega dt is equal to mu g over r, and then we multiply, I'm just going to cover up this w, multiply both sides by dt. All right. And we have a dw and a dt on both sides, so let's integrate both sides. So we're going to integrate dw from 0, d omega from 0 to omega, because the original rotational velocity was 0. It started originally with 0 as its rotational velocity. And then we started at t equals 0, so from 0 to t. So that's just omega is equal to mu gt over r. Pretty simple. Use calculus right there. See? It's not scary. Moving on to part C, it is asking us to just derive an expression for the time it takes the ring to travel the distance L. All right? Nobody panic, nobody panic. Distance L is basically from, oh, here we go. We have to look at what we already derived with that has something as a function of time in it. So we take what we know. Oh boy. We just take what we know and we write it down. We know that linear velocity is equal to the radius times angular velocity. We derived this equation here. We also derived this equation here. So we take this equation and we plug this into this side and this into this side. And what we get is v prime minus mu gt equals the radius times mu gt over r. And then we do some algebra, so we have the r's cancel. We move v prime over to this side. Then we divide both sides by t. We isolate the t, and then eventually we solve for t. So t is equal to v prime 2 mu g. And we know that t is the time it takes to cross distance L, because at the end of distance L, the linear velocity E is equal to v, and the angular velocity is equal to omega. It is not equal to v prime, because that starts... Sorry, it just thundered at my house, because v prime starts at the beginning of L. At the end of L, we have v. At the end of L, we have omega. Not omega prime, just v and omega. All right, onward to the next problem. Part D states, derive an expression for the magnitude of velocity of the ring immediately after it has traveled distance L. And you're thinking, wait, we already did that. It's right here. We just did that right there. However, this is still asking in only terms of these four and fundamental constants. But why could we have this answer here? Because it explicitly stated as a function of time. This does not explicitly state as a function of time, so we must have this expression only in terms of these four variables. Oh shoot, let me go get paper real quick. So since the question is essentially asking for this equation but without t, we solve for t here using the appropriate variables here. So what we do is we take t here and we plug it into here, and that should yield us the right answer. All right. So v equals v prime minus mu g t. T equals v prime over 2 mu g. So now we just solve this with regular algebra. Oh, sorry about that. It's supposed to be v prime. Prime over 2 mu g. This mu g cancels with this mu g, so we have v prime minus v prime over 2. So we have v equals v prime over 2, because v minus v prime over 2 is kind of like 1 minus 1/2, which is just 1/2, so v prime over 2. Cool, wasn't too terrible. Now on to probably the worst one I'm gonna say is E, so hold on to your hats, folks. Alright, part E, if you tried to figure it out yourself, don't feel down if you couldn't get it at first, neither could I. These calculus problems take practice when you're thinking in both terms of calculus and physics. When you get... Physics is so complicated. Well, I mean, there are just so many things you have to think of, and sometimes you just don't think of that. So, part E, derive an expression for the distance L. We start off simple. Okay, well we know that L, or aka known as distance, is the integral of velocity over time. And remember, the area under a VT graph, this area here, is the displacement or distance, and this is L. So the area under a graph is also the integral of the line of that graph. So we take the integral of the line of, or the expression of velocity in, with t, and we take the equation that we already derived in part, bi, and we plug that in for v with respect to t, vt. We take this integral, and what we do, we integrate it from 0 to t. And what we do is we integrate it in terms of t, so we get v naught t. We get from here v naught t, and then minus mu g over 2 t squared, because we already have a t, so it would be t squared over 2. Here's our equation for t that we are going to use later. And now we're going to integrate that from 0 to t2, so we're not even going to bother to write the 0 expressions because they're just all zeros. So we do v naught t naught. T is just final time I just had to do this, so we go from general t to the specific t that we need. So we have v naught t naught equals mu g t naught squared over 2. So we have that down. So all of our calculus is done so far. Now it's just algebra. And so now when we have t naught, we plug this in to our equation. So we have, v naught squared over 2 mu g minus mu g over 2 times this t naught squared. So we squared this whole thing and multiply it by this whole thing. And then, scribbles, the wonders of pens and making mistakes. We get v naught squared over 2 mu g minus v naught squared over 8 mu g, which is equal to 3 v naught squared over 8 mu g. Now, yes, so don't feel down if you didn't get that right away. I certainly didn't. Many people do not. That's why this is not an entry-level course. It is Physics C, and they do not expect you to know everything, which is okay. And the curve for Physics C is much better than the curve for Physics 1, so please don't panic about this. It's going to be okay. Just the better prepared you are, the more likely you are to get a 5. Alright, thank you for watching so much. Thank you for sitting through this nearly 30-minute long video. I really appreciate you listening to me. I'm sorry I speak kind of slowly and monotone sometimes, and sometimes I mess up. But I'll get you there. Alright, thank you for watching.